Hello, everyone. Thanks for having me today. And today's topic is about using the resistance corrosion high-strength stainless steel strand for pre-stressed concrete bridge elements. Before I start my presentation, I just wanted to share with you this picture, which was a coincidence. Usually when I test specimens, I just put them outside of the lab and then try to get rid of them. But one day I was looking for something else outside of the lab, and suddenly I've seen this picture, which shows both materials, the conventional carbon steel and the stainless steel. They were under the same condition, and you can see visually what happened to the regular carbon steel and the stainless steel, and that's give a reason why we are trying to study the stainless steel as a solution for corrosion problems. The corrosion, it could cause a real catastrophe in terms of bridges, and that's because of the, we could get this steel strand rupture, or even though in post-tension at the level of the anchors, and all these, corrosion issues would really either lead to catastrophe of the collapse of the bridge or the structural buildings, or would be high maintenance or would cost a lot to repair these buildings. And this is just a total annual cost for corrosion for infrastructure, which is 22.5 or 0.6 billion. And as a researcher, we tried always to find a solution for how to can have, let's say, a bridge that he could resist or could have a free corrosion problems. And we have several solutions. Today I'm just going to talk about stainless steel. We're always still ongoing working on FRP as a stirrups or as a strand as well. And our ultimate goal is to have a free or resistance corrosion bridge with these materials. Basically, some projects they've already completed using CFRP as a strand, GFRP as rebars, and those are the remaining that's ongoing. We have the stainless steel as a strand, stainless steel as a stirrups as well, and the FRP we use it for as auxiliary reinforcements. So that's mainly today's topic. I will try to talk in general because we've almost completed this project. And before that, it just mentioned the durability of these stainless steel strand, because it's not free resistance material. It's not free corrosion. It's resistance corrosion materials. Where research that been done, it's like 20-inch long pre-stressed specimens. They were exposed to marine environment for 20 months, and you could see the results basically where the stainless steel showed an excellent surface condition and there is no evidence of corrosion. However, I just spoke about the advantages of these materials, but when it comes to the behavior of these materials, I won't talk about the FRP. I will just mainly talk about the carbon steel, which is the convention that we use, and the stainless steel. The stainless steel has, which is the red one, has a lower ultimate strain, which is lower ductility. And that's the question that we want to address if we have this kind of lower ductility, because usually when we design our bridges and beams, we have our balance conditions. It's like when the concrete crash in the same time with the strand yield, and in this case we have the tension or compression control. But for the stainless steel, our balance condition is when the strand rupture, because we have the yielding, but between the yielding and the ultimate is very low strain reserve. So our balance condition is when the strand rupture in the same time with the concrete crashing. So in this case, we will have in the conventional carbon steel, we will have more deflection. So when steel yield, we will have more deflection, which means we're going to get the concrete crashing first. But in our case, which is using the stainless steel, we may get either the concrete crashing or strand rupture. Our goal here, the concrete crashing, which is controlled by concrete, so we don't have to worry about that. It's the same. But for the strand rupture, we need to understand what's going to happen. So this is just some section analysis where I wanted to just to show the differences between using these the stainless steel compared to the carbon steel, and that Dutch red line, which is, I mean, they have the same curvature. Basically, we used Type 1 with different strand, different number of strands, and you could see clearly when we, when we get, for above 7 strands, we have all crashing of concrete. They are almost matching, but when we had strand rupture, we had more curvature, which is we have more deflection. So that's the major research task. I'm not going to talk about the sectional and FEM. We just basically try to talk about the experimental program. Please stop me anytime, because I will try to cover all the experimental so far, but I know it may take time. So if 17 minutes done, I'm okay, because every subtask is a topic by itself. Basically, first thing first is we can get the mechanical properties of our strand, and we try to compare with the ASTM, and we did like several types with wedges or with our own anchors, and we got our modulus and the ultimate strain and stress. After that, since we talked about this lower ductility, which means we may reach this rupture, and the first topic was, are we going to be able to harp or not? Since harping, when we harp, our strand, usually we have more concentration of the stresses, which means we have more elongation. So this, for the FRP, we already tested, and we cannot, for the CFRP strand, so we cannot harp. But for this one, are we going to be able to harp or not? So that's the goal of this subtask here. So we already designed our test setup using conventional deviators that we have, either swivel or fixed one. And that's our blind prediction before we already test. So basically, there is a CFRP stainless steel and the conventional. So the regular carbon steel, basically, we could harp at any angle. But for the stainless steel, we can see here that we cannot harp at certain, because we lost like 50 or 60% from the jacking capacity, which is we get it from the uniaxial testing. And here, basically, what we got is a surprise, actually, and this is one of the tests using the stainless steel. We tested also the conventional carbon steel, where for the stainless steel, all the 7 wires, they ruptured. For the carbon steel, we got just 3, sometimes 1, 2 to 3, they ruptured. However, the stainless steel was too similar to the carbon steel in terms of capacity, not the strand rupture. And you could see the green one, which is CFRP, which has lower capacity compared to when we harp it at 15 degrees. But that's the only data that we have for the CFRP. So what we try to do is to understand why this is happening, since this one has lower ductility, so why we got similar to the carbon steel. So we went to go further, and we tried to understand. We took like the center wire from the strand for each carbon and stainless steel, and we tried to do uniaxial test just to see. And you can see the ones on the top is the carbon steel, and the ones in the bottom is the stainless steel. And you see the reduction in cross section for the stainless steel is higher than the carbon steel. And it has more localized strain than the carbon steel. Even the failure, it shows more brittle for the carbon steel comparing to the stainless steel. And that gives an explanation why in the FEM we got lower results comparing to the experimental tests. When we try to recalibrate because in the FEM usually we use either the extensometer that we have, which is 200 millimeters, or the strain gauges, but the necking or the rupture where it happened, that's where the localized high strain that we get. So we try to capture that strain, and you can see when we use the 1 inch, so I tried to orientate the rupture, so I reduced a little bit the section, and after that I did the tensile test to make it to the stress or the failure happen in between where the 1 inch, where I got this high strain softening. And that's explained why in the harping we got that kind of results. We recalibrated our FEM modeling, and we reached basically the ones on the bottom is the blind prediction that we did in the beginning, and the ones on the top is what we got after our recalibration. Another things that we have to worry about, which is the creep rupture. We talk about the creep But for the FRP, because it's brittle, the same thing here, lower ductility, at what stressing level we can go? So can we go to 80%, for example? What's going to happen after 1-2 years because we have that lower strain, so we need to understand what's going to happen. And that's what we did, actually. We tried to get some samples for certain pre-stressing level for 80, 75, 85, and even up to 90, which is in ASTM, we call them the 1 million hour test or 1,000 hour test, which is the 1 million is below 90% and above 90% is 1,000. This is just a summary. We, according to ASTM for the FRP, and since there is no for the carbon, there is no rupture because of the high strain. So we got, like, the blue one is the stainless steel. We have, like, 2 years so far. We tested 75 and 85, and no rupture appeared so far. So we have a limited surface life for this pre-stressing level. So we are confident to stress this strand at this level, and no rupture will appear. This is one of the samples that we forced it to rupture. We pre-stress it at 92% after 4,000 hours, which is 4 times the test time limit. We added 2 kips and nothing happened, and we just forced it to rupture. Another topic, which is the relaxation. The same thing. We have to know we've measured the relaxation to measure the losses. So we did the same thing. We tried to stress it at different stressing level, 60, 70, 80%, and these tests, they've been like for 2 years as well. We tried to measure the losses for each strand, each stressing level, and after that we tried to correlate and get our losses or relaxation losses. Also, we tried to confirm with what's in AASHTO, because we say for the carbon steel, when we are 50% stressing level, there is no relaxation, and we did the same thing. If you see the blue one involved, which is we pre-stress it at 50%, and it has like very, very low losses, which is we could use also. I mean, we confirmed that we can use what's in AASHTO equations for the relaxation. The same thing for the bond. I mean, here we are trying to, because the ultimate goal of this project is to have a guidelines, design guidelines, or for bridge elements when we want to use this stainless steel strand. So we did the same thing. We followed ISTM. We used the mortar, and also for further investigations, we used also the concrete, which is we use different concrete strength. And the same thing, we found similar results. This is for just an example for the 4 PSI, where we got this same full force test. And that's we confirmed, even though in the FEM when we used the same fraction coefficients and we got the same transfer and development length, because the bond has to do with the transfer and development. The next step after the we defined the characteristic for the bond between the concrete and the stainless steel strand. We did some small scale, large scale testing to measure the transfer length. And are we in our AASHTO, ACI, are they conservative? Not? Can we use these equations? Can we? Do we have to develop our own? I mean, we can use what's in ACI or AASHTO, but we're still working on developing our own equations when we use the stainless steel. This is just a way for the large-scale testing where we measured, and you can see the AASHTO, which is 60 dB, comparing to the experimental results in the dead and jacket end, which is almost a double, or let's say 2/3 from the experimentals. After we went to some mechanical properties, some small-scale testing, we go now to understand the global behavior, which is the beam itself. So we had like 13 large-scale beam, 40 feet, AASHTO type 1. I mean, we tested them at different type, loading, stress level, minimum reinforcement. We use slab beams where we want to get that balanced condition. We want to get rupture of the strand, concrete crashing. And also we did some post-tensioning to measure the wobble and friction coefficient. So these are some of the results. So what the first two on the top, basically we designed them to have strand rupture, and because of the lack of the concrete strength that we got in the precast plan, we got like our design concrete, it was 9 KSI, but we got only 7. So we got concrete crashing on the top. And the ones on the bottom, it was exactly what we designed, and we got a strand rupture. So what we noticed when we have this strand rupture, we have a big crack in the middle. But this big crack doesn't reflect what's going on in the post-tension, because in the post-tension it's different story, it's debonding, it's concentration of the stresses, and that one appears from the very beginning, but this one appears only at the failure. And basically, this is our test, and you can see exactly when the crack appears. It wasn't before, it's just at the level of the rupture the crack appears. So it has nothing to do with debounding when we talk about the post-tensioning. So that's what happened. That's the strand rupture. So here we didn't reach the maximum concrete strain on the top, so we didn't get that. And our goal is to have this strand rupture because concrete crushing is the same. This is the balance condition. It was a little bit hard to get this one, so we tried to get this same time, and you can see on the top it's concrete crushing, and after that we got strand rupture. So we wanted to get all the cases that we have: strand rupture, balance conditions, and concrete crushing. At the end, we tried to compare all the CFRP, the stainless steel, and the carbon steel. And you can see here the red one is the carbon steel, the conventional carbon steel. The black one is CFRP, and the blue one is the stainless steel. If we compare the blue one and the red one, which is they are the same except it has lower deflection, which is because of the strand rupture. So what we try to do is we try to design another one girder that we can get higher capacity, more deflection, and we can convert it to that because those three, they have the same strand, same total pre-stressing, and the same concrete strength. So we added like 4 strands, so they could be more or less the same. This is for shear test. After all, we also try to use some stainless steel stirrups for, and this is just the test setup where we try to because of our limits for our testing for the lab, we have the capacity of the actuator is just 230 kips, but we wanted 300 kips, so we just switched it a little bit. So we, instead of going down, so we went up here and we made like reaction frame. So we applied only 100 kips here, we got 300 there. So that's just for the test setup. And this is the shear test. Basically, this is not for the stainless steel stirrups. This is for the GFRP because we had GFRP, stainless steel, and regular stirrups. And I just brought this one here to share with you what we got in terms of when we talk about the VC and the VS, and when the basically usually when we say the crack appears, there is no contribution of the concrete anymore, and just the steel is carried everything. But here we try to do experimentally. Does the VC still contribution? And you can see here the VC is still contributing in our on the behavior of the. And here just a mapping using DIC. When we try to more or less analyze what's going on in the testing regions in terms of strain, we can get it at any level, crack width, and basically this would help a lot, even though we can get from here the stresses if we get the strain, and we're still undergoing to more analyze this data. And basically that's the last test we performed recently. And thank you for your attention.